Hello. Hello. Am I audible? Good evening, good evening, good evening. Hi, Abhi. All right. So, who's here? I guess some more people will be joining us. Hopefully. Okay. Am I audible? Am I audible? Do I start? Yeah. Good evening, Rashawn. Yes. Cool. 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 Okay, so I hope more people join along the way. My plan was to give you guys a quick rundown of circles. That is, I thought we'll start with circles because that's something people miss when they start studying for RMO, like geometry. They do triangles a lot, lots of configurations, but circles they miss. And there are lots of interesting circle problems. So I thought we will do that today. There are very few things to introduce about circles. The plan is that I am going to first talk about the theory very quickly, just to quickly remind you all the basic theorems, and then we'll just start solving problems. So basically we'll group solve it. You guys will tell me what to do as well. I will sit together and think. We'll practice a few problems. Okay, so that's the plan for the stream. So let's start. So here are some basic quick all the results about circles. Okay, so let's start. Here are the results. So results, some basic results, and you guys can remind me if I forget something. Okay, so one of the most basic results of a circle is that if you take a circle, right, then if you draw a chord, okay, then equal chords subtend equal angles. Okay, so that is one fact about a circle at the center. So if these two chords are equal in length, they will subtend equal angles at the center. That's one fact, very basic school fact. The other basic fact is essentially if you draw a circle and a chord, I'm finishing everything with a chord, and if you have a center and if you drop a perpendicular to the chord, that bisects the chord. Okay, simply because it's the perpendicular bisector. It's one of the definitions of perpendicular bisector. The radii are equal. Okay, so essentially the perpendicular bisects the chord. So this is another configuration. This is again the center O. So the third thing is essentially you take a circle. This is length based criteria. You can't just draw. So if you take two chords and they intersect, okay, at a point P, and let's say the chords are A, B and C, D, then something really nice is true. It turns out PA into PB is equal to PC into PD. Okay, the thing is that both of these are actually equal to the distance from, you can check that this is the same as r square minus OP square. Okay, this is the radius square minus OP square, where r is the radius. Okay, r is the radius. Then the thing is that actually something more is true, and many people forget that. It's very useful in actually calculations. People remember this because it's generally stated as a theorem, but this actually comes from something more basic, that the triangles are similar. Don't forget that, because there's a third ratio that people miss, which is useful in some problems. What a better thing to remember, in my opinion, might be, maybe you should remember both, but definitely you should also remember that these two triangles are similar. Okay, so PBD triangle is similar to triangle PCA, and the reason is pretty obvious. These are vertical opposites, so P is equal, and these angles are equal because we have not yet done that. part. Okay, so let's discuss that too. One of the basic facts about circle which I needed here for that statement was that angles in the same segment are equal. Okay, angles subtended by the same segment are equal. Actually, that is just a consequence of, if you like, this fact. If you know that if you know some more basic fact, that is that if you take a circle, then the angle subtended at the arc, and it's important that this happens only on the major arc. Okay, if the angle subtended on the major arc, if you take a point on the major arc, that is half of the angle subtended at the center. Okay, so if this is x, this is 2x. Supposing you are on the minor arc, that's no longer true, right? But you could also obviously apply this theorem to the reflex angle. So if you are on the minor arc, okay, then it turns out that you can apply the same theorem, but you have to apply it to the reflex angle. Okay, it's still true. If you apply it to the reflex angle, it's half of it. This fellow is half of this reflex angle. Or sometimes we'll just simply say that if this is x, then that's 180 minus, I mean, this, maybe we'll call this, so let's call this x, then this would be 180 minus 2x, 180 minus x by 2. Okay, that's because the remaining is 360 minus x, and 360 minus x by the whole thing by 2 is 180 minus x by 2. Because you can think of it that way. So using these basic facts, we can actually see that angles in the same segment are equal. Okay. However, it's a similar thing about being in opposite side segments is the following. That this angle x and y add up to 180. Right. So as we know, oh, hi everyone. So there are more people joining us. So hi guys. So the thing is that these two properties are defining properties. So let's actually color things that are defining properties. Okay. So for example, this is a defining property of a circle. If you could get two lines that intersect and PA into PB is PC into PD, then that will give you, in fact, you can say ABCD form a circle. Okay, so if you have this condition, this is a defining property. This is one way to show 4 points lie on a circle. This is another way. These two are also defining properties of circles. However, this is not. Okay, this is not. Be careful. Just because there's some angle x and angle 2x, it doesn't mean that the angle subtended 2x is the center, because there's a whole arc with angle 2x subtending. You can't tell which one is the center. All right, so these are some basic facts. Okay, so oh sorry, Balwant Reddy says please upload on your other channel too. Oh, you mean for the CUT channel? Yes, I think I should upload there. I stopped uploading. You're right. Maybe it's that. Okay. All right. So now I think all of you know the defining properties here, right? All of you know these defining properties. One of the things though that we will see in RMO, which is very useful, is that I think, I don't know, maybe we should do this today. We should also learn how to write proofs using directed angles, I guess. So that allows you to write proofs that are configuration independent. You can write it for one configuration and the arguments will go through for all configurations. Maybe we should try that. Yeah. Okay. Let me look at the channel. Yes, Balwant. Yes, I should. You're right. I just didn't find enough time to do stuff there, but I think I should. All right. So let's come back to one of the. So let's continue our story here. One of the things about directed, I think when we write proofs, I'll go back to directed angles. But let me just quickly revise more things here, which is needed for the problems today. And these are theorems that people forget. Okay. And these are about tangents actually. Okay. So if you take a circle, and if you draw a tangent, so if you drop a perpendicular from the center to the tangent. Krishan asks, what's the other channel's name? I forget actually. Maybe Balwant remembers. What is the name of the channel? I think I did it a few months ago. I give it some different name actually. Sneaky Scholar or something. Okay, I forget. Sneaky Scholar. Maybe if you search, you'll get it. So if you take, okay, I think I hope my audio is clear. Yeah. Is the audio clear? Okay. So it turns out that the radius and the tangent are always 90 degrees to each other. Okay. So that people remember, of course. That's not the one that people forget. The one that people forget is the alternate segment theorem. Okay, and even I'm guilty of forgetting it sometimes when applying. And it's a beautiful theorem. It's saying the alternate segment theorem states that if you have a chord and that chord makes an angle theta with respect to, I mean theta is just, it makes some angle with respect to the tangent at the touch point, then this chord subtends the same angle at the circumference, okay, on the alternate segment, that is on the other segment. So the alternate segment here corresponds to the fact that if you take this chord, it divides the entire problem into two regions, this region and this region. And the angle in one region is the angle subtended by the chord in the other region. You should understand why we say that, because you see this chord subtends one angle here, but it subtends a supplementary angle here from what we discussed. Okay. So which angle are we talking about when we say they are equal? We are always meaning the alternate segment, the angle in the alternate segment is equal. Okay. So at least that's the way I think about why it's called alternate segment theorem. All right. So this is a very, very useful result actually, and you should know how to apply it, and just make sure you don't forget about it. By the way, some other quick facts. Instead of saying two opposite angles are supplementary, sometimes we try to look at exterior angles. We say we extend this line and we say that this angle and this angle are equal. Okay, that's another way to say the same thing. Okay, and remember that these four are defining properties. All right, so these are some very basic facts. There's one more fact I forgot, and that's Thales' theorem. So Thales' theorem says that angle in a semicircle is 90. If you take a semicircle, this is a diameter, let's say, then the angle subtended is 90. Okay. Well, that's a special case of this really. I mean, when 2x is 180, then x is 90. However, the converse is also true. Okay, if you get if this is 90 degrees for a triangle, then the chord is the diameter. Okay. All right. So these are some basic facts. Now, slightly more interesting facts or more powerful theorems are the following. Okay. Let's quickly revise, and we need it for today's problem set. Okay. So this is about power of a point and radical axis. All right. So all of you hopefully know that the radical axis is the locus of all the points. Okay. So to define the radical axis, I need first of all two circles. Given two circles. I think I realized that I didn't define power of a point. Okay. So let's first do that. Let omega be a circle and P be a point. Okay. P be a point anywhere on the plane. P be a point anywhere in the plane. Okay. Then we associate a number to this pair. Okay. So let's draw a picture of it. This is a circle. Okay. And there is a point P associated to the point P, okay, and the circle. Maybe we should say, and sometimes we write omega bottom, but let's write it today together. Associated to this pair, point P and omega, we associate a number, this power. Power is a number. Okay, power is a number, real number. What is this real number? Well, we can say this in a variety of ways, but one way to say it directly as so that it looks clearly a property of P and omega is just to take the center of omega and you take the radius of omega, okay, radius of the circle omega. Then I can define what power of P omega is in terms of those two. So power of P omega is basically OP square minus R square, where R is the radius of the circle, O is the center of the circle. So what you do is you calculate this distance, you square it, you subtract R square, the radius square from it. Okay. So if you have O comma P, 2 points, this is called the power. But what is the main point? Okay, anybody can define this weird thing. Okay, quick note, okay, quick remark. I hope people are paying attention. Quick remark is that power can be negative. Power P omega can be positive, equal to 0 or negative. And if it is positive, P is outside omega, whatever that means. P is on omega, and this is P is inside omega. That you guys can see hopefully, right? I mean, if OP, the distance of P from O is less than R, then it's equal to saying OP square is less, minus R square is negative. Okay, so P is inside omega, the circle, then you have essentially positive, it can be positive, negative or 0. So now what is the point of this power of, I mean, what is the use of this power of a point? The remarkable use of this power of a point is the following. That is, if you draw a straight line, sorry, it says, just keep it below. Hope it's still audible. Is it audible? Okay. Cool. All right. So what is the beauty of this power of a point? It's the following. Okay. You draw any line passing through P, your favorite line you draw passing through P that cuts the circle. Pick any line L. This line can be any line, okay? Pick any line passing through P, your favorite line. So I'm drawing one of them. And suppose it cuts the circle at point A and B. Okay? Then the power of the theorem is that although the line can move and A and B can vary, the product PA into PB, well, the directed line segment PA into PB is always the power. And I want you guys to appreciate this. So when I say directed line segment, I mean the following. If P is outside AB, then PA into PB is positive. Think of it this way, like if you put a coordinate axis on this line, then if P were the origin, then A would be negative and B would be negative, right? So PA into PB would be positive, correct? So that's one way to think about how to think about directed segment. The best way to think about it is that if P is outside AB, then PA into PB is positive. And if P is inside AB, so here is another example. Let me draw another example for you. Supposing you draw a circle, and supposing you pick the point P to be inside this time. And again, you draw an arbitrary line that will cut. In fact, any line you draw here this time will cut because P is inside. Okay, so this is the line L, and this will cut the circle at 2 points again, A and B. Okay, now P is between AB. In that case, PA into PB should be considered negative. Okay, again you can see that in your coordinate axis. Imagine this was your you put coordinates, P is the origin, then B would be having positive coordinates and A would have negative coordinates. So PA into PB, when you multiply, you will have positive into negative will be negative. Okay, so you see that if you think in terms of directed line segments, then when P is inside the circle, PA into PB is negative. When P is outside, it is positive, and indeed as expected. Okay, but more importantly, the lens. Product of the lens, if you take the magnitude, is actually the magnitude of the power, okay, which is a really cool theorem. Okay, all right. Now, what is how can we use this and build more theory? The main thing to learn is we'll study the concept of a radical axis. Okay, so it turns out that if you take two circles, let C1 and like I used omega, so let's use omega itself. Like omega 1 and omega 2 be two circles. Okay, let P be a point in the plane. Now immediately we'll jump into problems after this. Okay, so let P be a point in the plane. Okay, then let P be, let's say, a moving point in the plane. Let P be that's important. Let P be a moving point. We want to define a locus, that's why. Let P be a moving point in the plane. Then the locus of all points P such that power of P comma omega 1 equal to power of P comma omega 2 is called the radical axis of the pair omega 1 omega 2. So given any two circles, okay, there was a question. So Viswanathan is, so what happens if P is on the circle? Oh, hi Viswanathan. So by the way, Viswanathan is some veteran. Viswanathan is a veteran INMO RMO person. He is my friend. So you guys can ask him questions if he's around in chat. Yeah, if P is on the circle, then indeed power of P comma omega is 0. Okay, and then when you draw a line, one of the points A and B will be P in the limiting case, indeed, as the B notes. Right. All right. So let's come back to this power. One of the amazing things about radical axis is that it's actually a straight line. It's not at all obvious. Okay, that a straight line is not obvious, and I'm not going to prove it, but I'm just telling you. Claim is that it's not immediate, but it's true that radical axis is a straight line. And you know, straight lines are really sweet because 2 points determine them. Okay, 2 points determine a straight line, right? Some of the most amazing things about straight line is that, and that immediately tells you when two circles intersect, what is the radical axis. It's so easy once you know radical axis is a straight line, because see, if two circles intersect, then we know that just now learned that the power of a point, as Viswanathan noted, that the power of a point is 0 if the point P is on the circle. So if two circles intersect, let's say they intersect at P and Q, then clearly since P is on both the circles, the power of the points are equal. They're 0 actually for both, and for Q also it is 0. So therefore P and Q lie on the radical axis. And since you know radical axis is a straight line, we are done, right? We are done. The common chord, the common secant rather, is basically the radical axis. So when two circles intersect, there's a nice description of what a radical axis is, the common secant. All right, really cool. But what happens if you know they don't intersect? Well, what if they touch? Well, that's just the limiting case. You can sort of imagine in the limit it will work. I'm just stating, I'm not going to prove things today, so I will wave my hands. So the thing is that if you take a common, in the limiting case, the common tangent is also a radical axis. Okay. So radical axis up to here is nothing new. It's same old characters that we know. But if two circles don't intersect, even then radical axis exists, and there is no other name for it. It's just the radical axis at this point. Okay. So radical axis is actually truly a generalization of a common secant or a common tangent. This is the locus of all the points such that the powers are equal. One cool fact about it is that it is perpendicular to the line joining the centers. Okay, that's useful to know. Okay, so it's perpendicular. And another key fact about this, which we didn't discuss, we should have done this in the limiting case when we talked about power before, which I forgot, was the following: that here again we can talk about the limiting case. As A and as you vary the lines, in the limiting case what will happen is that A and B will coincide. Okay, so in the limiting case when A and B coincides, let's say at some point T, right, then PA into PB essentially is just PT square. So you can also say this is equal to PT square, where PT is a tangent. Okay, so this is really cool about power of a point. We know multiple ways of computing the power. That's why this concept is so useful, because it has so many avatars, right? So here, this in particular means that if any point P on the radical axis has the following cool property, that if you draw a tangent to the first circle and you draw the tangent to another circle, the tangents are equal in length. Okay, the tangents you draw are equal in length. Okay, so all of these are just consequences. Okay, let's see, there are some questions in the chat. So is there some other invariant for the points on the common secant of two circles that you can generalize? No, I mean, it is a generalization. I'm sure there might be others, but it is a generalization, and it's an interesting, useful generalization. That's it. Yeah, you're right. There could be other generalizations of a common secant, although I don't know what it could be. It is certainly one of them. So I think Naban is asking, is it perpendicular bisect of the centers in the no touching case? Sorry, in the no touching case, is it the perpendicular bisect? No. Already in the common tangent situation, it need not be perpendicular bisect, right? Because this radius could be different from this radius. This and this need not be equal. The radius might be different already. Already it's not. It's not true. It's not a perpendicular bisect in general. But I think if the two radii are equal, maybe it is. Symmetrically, looks symmetric. Okay. Alright, so let's start out by the standard problem, and you guys can look at it, try for a while, and let me know what to do. So let's start. We will start drawing. You guys can type in chat the answer. So this is, let ABC be 3 points on a circle gamma with AB equal to BC. Let the tangents AB, I guess the more basic problem is which one? Maybe this one. Okay. So let's try to draw a circle roughly, and you guys can look at the picture. I'll draw it for you. You guys can stare at it, and we'll start solving problems now. So let's start solving problems. Supposing you have BA equal to BC, BA equal to BC, let the tangents at A and B meet at D. Okay. I'm going to draw it roughly. Okay. Oops. For some reason it's okay. So my thing is not reacting. Let's just see. So no battery maybe. Don't tell me. Oh, I forgot to charge it. Okay. All right. So I'll have to wait for a little bit of time. So let's see. So if you take tangents, let me draw it. I'll draw in a couple of seconds. It will charge pretty quickly. I think I charge it though. No, it's not even not charged. There's some issue in detection. So let ABC be 3 points on a circle gamma with AB equal to BC. Let tangents at A and B meet at D, and let DC meet at E. Prove that the line AE bisects segment BD. I can't see it. What is D? Okay, D. Okay. AE bisects segment BD. Okay. All right. So let's see. Does anyone have any suggestions? Please draw it yourself, since my Apple Pencil is not detecting. Okay. Oh, it's fully charged. Okay. Okay, finally it's working. All right, so let's do it. Thought for a minute it's gone. To buy a new pencil. All right, so now this is D, and what is okay? Okay, they meet at D. DC meets gamma at, what is gamma? Okay, this is gamma. DC meets gamma at E. Prove that AE bisects segment PD. Prove that if you join AE, second. Okay, oh, so let's see things in chat. Alternate segment implies angle ABD is angle BCA. ABD is BCA. Okay, so let's start seeing. I think there are suggestions in chat. So I'm going to follow suggestions in chat. What's the plan now? AE, we want to show bisects BD. Okay. I hope things we have written up to now is useful. So, sub B says alternate segment implies ABD. Okay, this angle is equal to this angle. BCA, that's correct. But these two are equal, so that's equal to this. So these two are parallel, I guess. Okay, so Viswanathan says try to show DE is equal to EC and that AE is parallel to BC. Okay, AE is parallel to BC, he says, and then DE is equal to EC. Okay, all right. So then by midpoint theorem, I get it. So essentially, then by midpoint theorem will be done. Correct. So that's Viswanathan's suggestion. So let's see. Let's try to prove this and this are. This is, I think we already know these two are parallel, but we have to chase some other angles to know these two are parallel. So I guess this angle here and this angle here, we should be able to tell are equal. Another thing is to show DE is equal to EC. DE is equal to EC. Let's see, how can we say DE is equal to EC though? I think we have to use, okay, so let's see, what do we know? We know that this angle here is equal to this angle. Angles in the same segment are equal. Is this, okay, so if what Vishwanath is saying is true, if they're parallel, then this again is again isosceles, is it? So if you have these two angles are equal, right? It has to be then these two angles are equal. So why are they equal though? So we certainly know these two angles are equal. So how do we prove these two angles are equal? So Abhidnya says, okay, oh, multiple people have said things. So Abhidnya says DBA is the same angle. Yeah, they are all the same angles. That's correct. I have marked them. That is indeed correct. I do an accurate diagram, but D is not equal to, so maybe I'm wrong. Okay. So that's what, I don't know whether it is true, but it could be. Is it true if you reverse guess? Then it will form a parallelogram, no? This will become a parallelogram. Is it true that this is a parallelogram? I don't know actually. I can't disprove it. So Nabhan is saying, can we try the midpoint theorem proof? What midpoint theorem proof, Nabhan? Which one are you talking about? So again, I think we need parallelogram, right, for midpoint theorem proof also. It depends on which midpoint theorem proof you are talking about. What have we not used here? Let's see. So actually my diagram is not, is it very accurate? If it's accurate, I can measure here only. D is equal to EC. I think it might be actually. Although I don't know whether my diagram is accurate. BC, is it equal to AB? It's almost close. And tangents look tangent to me. Yeah, I think it's accurate. Maybe DE is equal to EC. That he is right. So how do we show this? So if you could prove E is the midpoint of DC. I think you can show the following. 180. How do we do this? X. Should we start labeling and running around chasing angles? So Abhi notes that dA is equal to dB. Oh, I see. So I guess I didn't mark that. Is that the reason we are not getting it? Yeah, you're right. dA is equal to dB, we already know, right? Tangents are equal in length. So therefore these angles are equal. That's correct. These angles are equal. And that is true. So this is indeed the angle bisector of this angle. This is the angle bisector. So what? Oh, sorry. Is there some comment? dA equal to dB. So DAB is equal to ACB. DAB. Oh, okay. DAB is equal to ACB. That is correct. So these two cannot be equal. If these two were equal, is that what you're saying? No. I know what you're trying to say. So D equal to dB is trivial. That is true. Join BE and power of a point. Yes. So I'm hoping to use power of a point. I thought we'll use power of a point because I saw tangents, but I don't know how to use it though. What power of a point? DE into DC is dB square. That's for sure. That we can use. We have to show, another thing is to label them F and show the power of F, FB square is equal to FD square. So FB square is FD square is what we have to show, and FB square is a tangent to something. Can we use that somehow? So FB square is FE into FA. So FB square by power of a point is FE into FA. We are supposed to show FB square is FD square, which means if we could show FD square is FE into FA, we are done, right? Wait. So is this what Viswanathan is saying? Maybe join BE and join BE and do power of a point. Well, how will BE and power of a point help? I think this itself is power of a point, right? FD square is FA into FA. Can we say no? Yeah, that will not work. FD square is FA into. What does that mean? So I think, okay, yeah, no, but let me try some other thing. I think I remember now. I've done this problem before. I've done this. Okay, all right. So fine. I guess I know how to do it, but let me try strategy in the chat. What are your suggestions? I think AE parallel to BC is a thing wrong because this would imply AB equal to AD. What is wrong? AE is parallel to BC is wrong, because if AE were parallel to BC, then what will happen? Then these two would be equal. What's the problem with that, Abhi? Why would AB equal AD if AE is parallel to BC? I don't see why. AF would be the angle bisector of what? If this would be green and alternate segment on point A. I mean, alternate segment on point A tells you that these two angles are equal, which we already know, right? Angle subtended here is equal to the angle here. Yeah, not true. Okay, so I think I know how to go about it. I sort of remember it now. But the thing is that I don't know. I mean, I just remember that this is what you could do. FD square is FE into FA, power of a point. Okay, FD square is FE into FA, which means that we just have to show, we have to prove this. To prove this is the same thing to prove as take a circle passing through ADE is tangent at D to B. I mean, BD is tangent to it. If you could prove that, we are done. if you could argue that D is tangent here, if you take the circumcircle, can we prove? Can you guys come up with a proof? Circle AED is tangent to BD at D. Can you prove this? Then we could use, then we are done, right? We can then say FD square is FE into FA, but so is FE into FA is also FP, so therefore FD equal to FP, and we are done. So Rishan is like, what motivates FB? I just motivated it, right, Rishan? So basically we wanted to use power of a point, right? So clearly FB is a tangent. So FB square we know is FE into FA. There's only one secant passing through F. So we wanted to apply power of a point at F. So FB square is equal to FE into FA. That's for sure. However, we are asked to prove FB square is FD square. That will force FD square to be, if it is true what we have to prove, then FD square is FE into FA. But FD square is equal to FE into FA means that circle AED is tangent to D at, so the BD is tangent to circle AED at D. But that maybe you can do by angle chasing, some angle, something, I don't know, I don't know still actually. Maybe that angle chasing is also as hard. What do we have to prove? What do we have to prove? We have to show, what do we have to show? We have to, what is a chord here? DE is a chord or AD is a chord, some chord we have to choose. AE chord maybe. DE chord, this we have to prove this angle is same as this angle. Then we are done. Then alternate segment theorem. Converse of alternate segment theorem. I didn't say, but converse is also true. Yeah. FDC is FAD. Yeah, FDC is correct. FAD, that's correct. Or this, which one is better? I don't know. This angle is the angle subtended on the other side of that circle, which is 180 minus, if this angle is x, then it's 180 minus x. So this angle is x, then this is 180 minus x, something like that. Or which is the third one? Okay, no, there are only two chords. Only two chords passing through D. So I generally tend to write everything that is possible because I never know which one helps. I try for a while one of them and then the other. So let's see which one will help us. Which one do we know? I think I'll take this one because I can use stuff about this angle. I can use the black angles. The black angles have a name. If I give black angles a name, x here, blue x, x and x here, lots of x's, then I can try to do, I can check whether this chord satisfies alternate segment. I mean, it's one or the other, but this one is the beneficial one because this angle we know, I'm assuming, I'm hoping. Okay, let's see. So this entire thing we know, right? 180 minus 2x. But how do we tell what this is? We're done, I think, right? We're done. So this is also 180 minus 2x. So this is 180 minus 2x. So what remains is 2x. So if this, you take a point on the circle on the other side in the alternate segment, by supplementarity 2x, this will be 180 minus 2x. So therefore, the angle subtended by ADF is also the angle on the other side. So by alternate segment theorem, AD, the circle AED is tangent to BD. Is that fine? Does that seem reasonable? Yes, I mean, I've done this before. Okay. Any questions? I guess this is fine. All right, so maybe I think I've picked random problems, so hopefully I've not seen this one. So let's again start. Okay, so new problem. Okay, I hope I have not solved this one. So let's sit and think about this. So S and T are two circles that touch at X. S and T are two circles that touch at X. Okay, S and T. They have a common tangent which meets S at A and T at B. Okay, so there's some common tangent. Oh, drawing common tangent is a bit of a pain. Okay. Okay, so you believe me, it's a common tangent. It's not actually. So S at A and T at B. The points A and B are different. I mean, yeah, they're saying it's not equal to at X point, I guess. I'm assuming they are touching externally. Okay, they didn't say that. It could be touching internally. Let A and P, let AP be diameter of S. Okay, P is the diametrical opposite point to S. S is the name of the circle. Prove that BXP lie on a straight line. Prove these are collinear. Prove BXP are collinear. Okay. Guess what is the natural thing to do? Join. That would be. This seems maybe it's an easy question. So BMO question. I think I was copying all BMO questions. I think naturally you join A and X, no? And they have told you AP is the diameter, so you know this is 90. So if all it remains to do is prove this is 90, then we are done. They add up to 180, right? So could we argue this is also 90 somehow? Could we argue that AXP, again some, can I use some alternate segment theorem or something? So this is a chord, this makes an angle something, or this is a chord, the angle subtended with the chord is this angle X, and if I could prove this is 90, I would prove this is 90 minus X. So the bigger triangle is right angled. The bigger triangle is also right angled. I see. That's correct. I see, we are done, right? Zabednia solves the problem, noting that this is diameter and this is tangent, so therefore they are 90. So we are done actually, proof is over, right? What is the reason? Because this, if it is X, then this is 90, okay, and this is 90 minus X, then this is X. Oh no, it's not over. We still have to prove this is 90 minus X, then we will get this is 90, right? So how do we prove this is 90 minus X? I think this is a common tangent. So can we use that somehow? And again, alternate segment theorem maybe. Wait, so Rishon says the center and X are collinear. Yes, that's true. Do you want to use that? We could use that. Okay, we could use that. So the angle subtended, although I don't know. So let's see what other things. Abhinay Singh using similarity. The inner two triangles are right angled. Abhinay, we don't know BXP are collinear. So Nabani was saying, Nabani, what did you say? ASP for APB. I don't know what you mean. What I mean, S is the name of the circle. I don't know what you mean by ASP. S and T are names of circles. P, X, A, B are points. We have to show these circles. So in other words, somehow we have to argue this is 90, right? We have to, I think, use what that these are. Let's see. So these three are equal in length. How do we argue this is 90 though? How do we argue this is 90x? PAPB. Oh, is that correct? Can I do this? From x, if I draw the common tangent, the common tangent is a radical axis, right? And the radical axis will bisect AB. Is that correct? Let's call it, let's see. Let's say you draw the common tangent at x. Okay, you draw the common tangent at x. I know this is a nice proof, but you draw a common tangent at x. It will bisect AB, we know. That's a property of radical axis, right? Because this, by the way, is the radical axis of the two circles, the common tangent, and any point on it has equal powers. So PA equal to PB. I mean, PA is the tangent to first circle, PB is the tangent to the other circle. Length of the tangent square is power. So powers are equal means tangents are equal in length. So basically, this is a good fact to know. If you take a circle, it's better to by heart this fact. Okay. So if you take two circles, then we take the two circles and we draw a common tangent to them. The common tangent is bisected by the radical axis. Okay, if you have a common tangent that's bisected by the radical axis, the drawing is so bad. If you draw the common tangent, it bisects the radical axis bisects the common tangent. These two are equal in length. Okay, so that's a fact worth memorizing. So that if you apply here, you'll see that these two are equal in length. These two are equal in length, but tangents drawn from a point are equal in length. X and A are both tangents. So these three are equal in length. Now we know the famous configuration, right? If you have three lengths equal like this, this is 90. So we're done. Oh, sorry, I got excited and I started talking. So what did you guys do? All right, so it gives you AX01 as isosceles. I think you guys wanted to do it in some other way, so you can try. AX01 is isosceles. Yeah, I mean, indeed. So these three are equal in length, that we know already. So by the way, I think I used two facts, two things that you have to memorize. Okay, all of you. That if you see in a triangle, when you join the median, okay, if you draw the median, you see three lengths are equal, then instantly you should memorize that this is 90. Conversely, in 90 degree, that is again true, that the median and the opposite side, half of the opposite sides are equal. Okay, the median is equal to half the opposite side in a only in a right angle triangle. Abhidna is asking why three same lengths imply 90. Thales theorem. Thales theorem, Abhidnya. If you take this as the center and this as the radius, then when you draw, it will pass through the remaining 3 points. So do you guys see the proof? It's pretty nice. That one and the other one that I told you guys. That is, I think maybe we should draw it in GeoGebra and see that it bisects, right? So where is GeoGebra? GeoGebra, I summon you. Let's see. So let's draw it in GeoGebra. So you guys see it and memorize it. Okay, it's a very nice fact about, very useful fact. So if you draw, so let's get rid of these points. And let's draw the radical axis. I thought there was a radical axis line here, polar or something, tangents. No, there is no radical axis line. Okay. So let's take the intersecting points. That's the radical axis in this case, right? The common secant. And let's draw a common tangent. Okay. That we can draw easily in GeoGebra. Just pick the two circles, we'll draw every common tangent. I want you guys to pay attention to this here. Okay, let's forget the other common tangent. Just focus on one of them. Okay, so if you notice here, all I'm saying is the line EF bisects GH. Okay, so let's see whether that's true. Let's see whether that's true. Let's look at compute the length of distance from I to G. IG is 4.24, and let's compute the length distance from I to H. It's also 4.24, as you guys can see, because you can also draw the midpoint and check. Okay, so it's really useful and worthy to memorize that the radical axis always bisects the common tangent. Great, right? Okay. So what happens when the limiting case when E and F coincide? Okay, so very difficult. Okay, very close now, E and F coincide. In this case, what will happen is that, as Abhi notes, what we proved just now, GI, FI and IH will become equal if E and F coincides. So you always have 90 degree, that's correct. The three tangency points together always form a right angle triangle, always. Really cool. Okay, awesome. That's what this question is about, at least the way I did it. I don't know what are some other ways to do this. Okay, by the way, this is some random BMO problem. I really have not seen the solutions of this, I'm promising you. Okay, I just looked at the questions and I copied it, and I'm happy that it used the stuff we learned today. Okay, so let's solve another problem. So if you guys have alternate solutions, you can always put it up. Okay. All right, so let's try another question now. This also has circles and tangents written throughout, so that's why I just copied it. This is another BMO problem. So let's try it. Let ABC be a triangle. ABC be a triangle. Let ABC be a triangle. Let S be the circle passing through B tangent to CA. Circle passing through B and tangent to CA at A, meaning it's passing through B and A. Oh god, just drawing this is a bit of a... Drawing this will be a problem for me. S circle passing through B and tangent to CA at A. And let T be the circle passing through C tangent to AB at A. Okay. I apologize, but something like this. It's tangent here. Okay. Tangent A is a common tangency point. Right. Okay. The circles S and T intersect at A and D. Already it intersects at A, it also intersects at D. Let E be the point where the line AD meets circle ABC. Okay. More circles. I think this is some modern BMO problem, not old. I picked randomly. So, okay, this, I think I should draw it in GeoGebra. You guys should really draw it with your straight edge and compass, maybe. Okay, E, bad drawings. D be the point where line AD meets circle ABC. Prove that D is the midpoint of AE. Okay, you have to prove D is the midpoint of AE. So you can draw it in GeoGebra and then come back as well actually. So what do we have to do? We have to start with the triangle ABC and draw a circle that is tangent to I guess you can draw two circles which are intersecting and then draw tangents and then draw the circle first, then the circle, and then draw tangents at that common point, two tangents. They'll intersect the circles at B and C, and then get the triangle and then draw the circumcircle. Well, let's try to reason for a while on the bad drawing, see if we can get anywhere. In a couple of minutes, I'll draw it on GeoGebra if we can't get anywhere. So what are some strategies? What might be the plan to prove D is the midpoint of AE? D is the midpoint of the chord. Right? That's the same as saying the perpendicular bisector. If you take the circumcenter of ABC, join O to D, it's perpendicular. Maybe it's some angle chasing using that, maybe. Also, how do we use the fact circle B is tangent to CA at A? So Rishon says aren't BDC collinear. What? Why? Because by Thales theorem, ADB, Thales theorem. Sorry, AB is not the diameter. Rishon, I'm sorry, am I wrong? AB is tangent to that circle. I mean, we should name the circles. Let's call this circle omega 1. And let's call this circle omega 2. Intersection of omega 1 and omega 2 are A and D. And AB is tangent to omega 2 at A. So what do you mean by Thales theorem? AB, AC are diameter. Why are AB, AC diameter? Vishnu, can you explain why AB, AC are diameter? Okay. Okay, so I think we can do this now, like alternate segment maybe. Can we? Can we alternate segment it? Like if you take this and AB is tangent, this angle is, what do we know about D is the midpoint of E? Power of a point is not very useful, I think. Okay, this is the radical axis is for sure. Can I use that somehow? This radical axis. dA is the common chord. dA is a common chord, that's true. This drawing is so bad, maybe. Okay, can you join BD and CD? Yeah, I think so. I should join. Okay, so let's try and join that BD and CD. Now what? The drawing is terrible. It's not telling anything. So remember, this is tangent. This is tangent to omega 2. The brown line is tangent to omega 2. Maybe we should write it in that color so that people can understand. Brown line is tangent to omega 2. So if you take any chord, the angle subtended here or the angle here, which is the angle A actually, the triangle is 180, this is A, so this is 180 minus A. Maybe that's useful, right? We know this is 180 minus A by alternate segment theorem, because this is the angle A. AC is a chord, right, in omega 2, and similarly on the other side, right? Similarly on the other side, you have this chord AB, it subtends, and the alternate angle it will subtend angle A, but that means this is 180 minus A, I don't know if this is useful though. So this is 180 minus a and 180 minus a. And obviously because of triangle ABC, this also is 180 minus a. I don't know, I'm just telling you guys all the things that are 180 minus a. 360 minus 2a, so this is 2a. Oh, this is 2a. That's the same thing that even circumcenter will have. This also is 2a. Certainly VDOC are concyclic, that we can tell. Center of the circle, O is the circumcenter of ABC. I might be wrong, so you guys should talk and tell me if I'm wrong and just correct me. I think this is correct up to now. Alternate segment. So can we say something? Maybe we should introduce the point O. Maybe we should introduce the point O. BDOC are collinear. Sorry, concyclic. I'm sorry. Can we argue? All we have to argue is OD is perpendicular to AE, and we are done. AD equal to DE. Just show this is 90. Any plan you guys have? Why is this 90? Oh, this is 90. I think that's saying something about this line. Okay, this angle is A and this angle is A. Does that help? So you just have to show this is 90 minus A. Why is this 90 minus A? But they are concyclic. So showing this is 90 minus A, same as showing this is 90 minus A. But that's trivial. Done. Awesome. Okay. All right. So let me demonstrate. I think my proof is over. Okay. So I'm going to write it out for you guys. So is it clear to all of you, first of all, that 180 minus A, 180 minus A? Is that clear to everyone? Okay. Is that clear? Why these two are 180 minus A? Or maybe I'll draw it on GeoGebra, okay, so that you guys can see the proof clearly. But I got my proof. So new, discard, geometry. I'm going to explain it to you guys now, the proof. Before that, let's draw that annoying drawing. So what should we do? We should take two circles. And we should get rid of unnecessary stuff. Okay. And let's call this point. In the problem, this point is, well, we'll keep it like that and I'll remove the labels later. Okay, so let me draw tangents to this line, tangent to this line, and this is basically the B and C. I'll just name them whatever right now and I'll remove the labels and I'll relabel them. And then you have to draw this circle about like this. This is our ABC circle, and then don't worry, I'll just label it and you guys will know properly what is going on. It's just right now not clear. So okay, as you can see, EH equal to HI. Okay, so that's what we have to do. So no, let me remove the labels first. It's confusing. Show hide labels. In fact, show hide objects only will hide the objects. Oops. Okay. Great. So oops. Show hide objects. There's an extra object missing. Okay. All right. So now we will transfer. Okay, and we will go to notability, add to geometric prep. Okay, I think it's somewhere transferred here. All right, so we are ready now. Cut. Let's erase this entire thing. Great. Okay, all right. So let's now solve the problem. Please let me know if you don't follow at any point. Okay, so let me label all the points now. This point here is A, okay, and this point here is B, this point here is C. So now we have the triangle ABC, green color triangle ABC, okay, given to us. I think this okay, so we have a triangle ABC given to us. S is the circle passing through B tangent to CA. So this is S. This is S. Okay, this is S. And similarly, this is T. Okay, circle passing through C that is tangent to AB at A. Okay, and the circles S and T intersect at A and D. So our point D, we should not use some black. So let's say this is D. And AD extended meets the circumcircle ABC at E. Okay, so now you have to prove AD equal to DE, and it looks like that AD is equal to DE in the drawing. Okay, so what is the plan? So let me just quickly explain to you what is my proof. My observation is first the following. Okay, so I want to construction join BD and DC. Okay, join BD and DC. Let's erase this and write it bottom because it doesn't obstruct our calculation. Okay, so we want to prove D is the midpoint of AE. Okay, so let me know if you don't follow anything, ask me questions in chat, but the plan is to show this is equal to this. For that we are going to chase angles now after joining. So I am going to use angles in the same alternate segment theorem. Notice that this is a tangent to circle S and this is a chord. Okay, so by alternate segment theorem, this angle, the angle made by the chord, the secant and the tangent is the angle subtended in the alternate segment. This angle is what we call angle A of the triangle. So this angle is A, which means it's the angle BDA must be 180 minus A because it's supplementary, right? It's opposite angle of a cyclic quadrilateral. So therefore we learn first thing, this angle we learn is 180 minus A. Okay, I think I should write it in bold because all this so 180 minus A. Okay. Very similarly, the other one is also 180 minus A. Same proof, same argument, but symmetrically on the other side. This automatically means this D has nowhere to go. Okay, anyway, it's fine, I write on it. So this means because ADE are collinear, this angle is A and this angle is A. Okay. Now, a nice thing about this we note is that BDC is 2A. One thing is BDC is 2A, but we know another thing that subtends 2A, and that is BOC, because the angle subtended at the center is 2 times the angle subtended at the arc. So this is BAC, which is A, and if we take the center of the circle, which I didn't draw, the center of the circle somewhere here, the center of the circle O, then we know that BOC is also 2A. The fact that BDC is 2A and BOC is 2A means that BDOC are concyclic, right? BDOC are concyclic, and once you get BDOC are concyclic, remember we have to prove AD equal to DE. In the circle ABC, AE is a chord. To show D is the midpoint of AE is the same as to show if you drop a perpendicular from the point center of the circle to the chord, we know it bisects the chord, right? So it suffices to show OD is perpendicular to AE. Okay, suffices to show OD is perpendicular to AE. So all we have to do is join OD, and all I have to do is prove that this is, this entire thing is 90. But I already know this angle is A. So all I have to show is this angle is 90 minus A. So I have to show suffices, it remains to show ODC is 90 minus A. Okay, that's all I have to show. Now notice we know BDOC are concyclic, we have not used it, so we can use it now. We have to show this is 90 minus A, but since they are concyclic, that's as good as angles in the same segment. I have to show OBC is 90 minus A, but that's trivial actually. So OBC is 90 minus A is trivial because if you take a circle, this is standard configuration, right? So if you have A, okay, if you have any triangle ABC and you have the center O and you take BC, then remember O is the meeting point of the perpendicular bisectors, so you can join here, you will get the midpoint, and you know that this angle is A, this is 90, so what remains here is 90 minus A. So you know that the angle OBC is always 90 minus A. So we are done. So OBC is equal to ODC. This is true because angle OBC is 90 minus A and BDOC are concyclic. Okay, is this proof clear? Any questions? I think this is a nice question. So it used, see what facts did it use? It used alternate segment theorem. Then it used the fact that if angles subtended are equal at B and C subtend angle 2A at both D and O, so BDOC are concyclic. That another fact about circles it used, right? Then again we use the same fact. Once you know BDOC is cyclic, we used angle ODC is angle OBC. And finally, we should know standard configurations. That angle OBC, we should know that we know to calculate angle OBC. Okay, this is basically reduces down to this philosophy that if you have a triangle centers like the orthocenter, circumcenter, incenter, you can calculate all the corner angles in that configuration. So the moment I realize that I reduce the problem to AOBC, I know that okay, I can calculate the corner angles. Then it's just a matter of chasing. Okay. So knowing configurations very useful. Okay, so I won't redraw it, but maybe in some other set I'll do it. But you should try to chase all the angles in the orthocenter. A, B, C and H you draw, and you join H to A, B, C and so on, and try to chase all angles. With O you can do, with I you can do, in center. You can't do it with centroid, but other things you can do. You try it and remember it. So Naban is saying, can we say that BDC is 2BAC, D is the circumcenter, BDC is 2BAC. No, right? It's not. The converse is not 2. I said it at the start actually. If you remember, this converse fails here. See, here the converse fails. Only for blue things the converse is 2. Here the converse fails. You cannot. There's a whole arc, no? Nabanyu? There's a whole arc here which all subtends 2x. Locus of all the points which subtends a given angle is a part of a circle. So you cannot. Okay, cool. All right. Maybe we can solve one more question, and which one? This one or this one? Other ones we can give as homework to try. So one more we'll think about. Again, another British Math Olympiad problem. Let's try this. You guys have to tell me now. I'll give you a couple of minutes to try this problem. You can try to draw it. Circles S1 and S2 meet at L and M. P is the point and S2. K lies on a fixed circle. Okay. Maybe I should draw it actually. Maybe I should draw it. Circles S1 and S2 meet at L and M. You guys draw it with me on your notebook. So S1 and S2 are two circles. It's too thick, I guess. They meet at L and M. And P be a point on S2. Okay. PL and PM meet S1. Okay, PL. Maybe I should draw it in a. This is not a good point to draw P, I guess. Maybe I'll draw P here. So I want to join PL and extend it. Meet S1 again at Q. Okay, and R respectively. The lines QM and RL meet at K. QM and RL. It looks like it's on the circle. Maybe it's not actually. This is bad drawing. Show that as P varies on S2, K lies on a fixed circle. As P varies on L2, K lies on a fixed circle. I guess if you could show something like LKM angle does not change or something, we are done, right? Angle LKM might just be a property of something. As P varies, maybe LPM. LKM is a property, is a function of LPM, then we are done. Because LPM is not changing, right? As P varies on the circle. Oh no. If P goes to the other side. So V wants to do a coordinate geometry proof, because when you see that things lie on a fixed circle, you feel like using coordinate geometry. I guess you can, but it can get, yeah, I guess it can get complicated. Because let's see, how will you set it up? You have to start with two circles, then you have to find either, yeah, how will you do it? I guess you can use abridged coordinates, but it's a good question to use abridged coordinates, I think. I think this might be a problem where it's better to use directed angles. But anyway, first let's try to run an argument, come up with a strategy. I guess something like LKM does not change the angle or something should be the plan. I don't want to draw it in GeoGebra because that would be like cheating. We can see the locus clearly if you try to move it. If you try to move it on GeoGebra, if you just keep a single drawing, it's fine. But I guess this drawing is not bad. It's quite accurate. So what would we do now? What do we know? PLQ are collinear, PMR are collinear. I think we can chase angles. There's nothing in this problem, right? Two circles meet at L and M. PL and they go and meet at R. Yeah, this seems very general. Why is K moving on a fixed? Why don't we just call this angle alpha and start chasing? I guess that's it. Maybe there's nothing more. Join LM, maybe construction, because a common chord, right? Very useful. Join LM, then maybe join QR also. Then you can transfer angles, right? This angle is equal to this angle. So Abhi is asking, what about LKM being a function of LPM? Yeah, so we know this angle is equal to this angle and so on. So can we somehow get LKM is actually 180 minus QKL, or LKM is 180 minus KLM plus MKL. Maybe that's better, because KLM is RLM and RLM can be transferred to RQM, and we can do something. We can transfer this angle here, and we can transfer this angle here. Okay, but that's not helpful. And that's same as saying this angle, same as this angle. 180 minus. So that's obviously trivially true. What other things can we do? So, or we can do exterior opposite angles. This angle is essentially this plus this. That's useful. This is 180 minus this. So we can move to the other circle, and then we can again start transferring. Should we do something like that? So this angle, what do we know about? The same as this angle. So these two angles are equal. And once you have this angle and this angle, done, I think, right? Done. Can we try? So let's try. So angle LKM. Okay, I don't know. Okay, I'm just trying. So angle LKM is angle by exterior angle is sum of interior opposite angle. Angle LKM is angle KQL plus angle KLQ. Correct? KQL and KLQ, this and this. The hope is that from there I can use angles in the same segment. So I can say this is same as this. So KQL is really the same as LRP. Oh, wait, there is some strategy in chat which was there some better way to do it? KLQ is 180 minus RLP. So 180 minus RLP. But I like this because it's like LRP and RLP is coming, right? So I thought something will happen. Maybe I'm wrong now. LRP, or I didn't even need that, I think. Okay, anyway, LRP and RLP, if you do 180 minus, what do you get? Is this correct? It's not useful, I think, because I guess LRP plus RLP is 180 minus alpha, but I get a negative sign here. Is there something else that's constant there? That story as p varies over the circle. LPM was constant, so I thought that's good enough for us. I think it should be related to that. LRP, I made a mistake. KQL plus KLQ is LKM. That's correct. KQL is LRP. KQL is MQL and MQL is MRL. Okay, that is this angle, and KLQ is this angle. This plus this, yeah. So adding. If it was subtracting, again exterior angle I could have used. Should I use R? Should I have used KLQ is RLQ and RLQ is RMQ? Would that have helped instead? Abhi says, I have a hunch locus is S2 itself. No. I doubt it. My drawing, don't trust my drawing, I told you, right? Like, it's I've drawn using too thick. So KLQ is RLQ and RLQ is RMQ. Maybe that is useful, I don't know. LRP and RMQ. LRP and RM. No, not useful. So I don't know. What do we do here? RMQ is LMR minus LMQ. LRP and I have to keep writing. I think LRP. I'll just keep writing. You guys can tell me if I don't know what to do. So QRP. It looks like there's nothing much in this problem. So then I don't know what more to do. So you just chase angles. LRP is QRP minus LRP plus RMQ is, what's RMQ? It's RML. I want to use that L number more, that's why. RML minus QML. Sorry, QRP, this is LPP I've written. LRP is QRP minus LRP. Okay. So why am I doing all this? So the thing is, what is remaining constant here? As P varies, I think only QPR is remaining constant. Somehow can we write it in terms of QPR is the question. LRP, what is LRP? LRP is LRM, which is LQM. LQM that is just minus MLP QRP. Oh, is it simplifying? QRP okay, so maybe you guys can correct me. So LRP and QML. LRM is same as LQM. I hope I'm not going backwards. So you see, LRP, this fellow, is same as LQM, and this is QML. So you have LQM and QML adding up. Okay, here these two are adding, which is nothing but by exterior sum just MLP. See, now I'm getting in terms of ML actually. It's what I wanted. So this I can write the sum as in the negative sign as MLP. So let me just write it, and I'll explain to you guys later if you didn't follow everything. RML minus MLP. Now we got MLP, and how to use the remaining though. RML is RML is okay. RML is 180 minus LMP. This QRP remains, no? It's not nice. QRP, RML is supplementary to LMP. So 180 minus. I think I made a mistake somewhere or something. I don't know. Because this now 180 minus LMP minus MLP is just PLM. So I'll get QRP plus LPM, which is what I wanted. I think LPM is not changing. As P varies, LM is fixed. As P varies over S2, at least in the upper major arc here, this remains the same. So this LPM is not changing. But I have some extra term QRP. I might have made a mistake. So you guys should ask me in chat now where I might have made a mistake. I have not used, no, this is useful. This LMR, I could have also said is 180 minus RQL. Minus RQP. Hi. Hi, Adi. Claim by angle chasing LKQ's LPM is fixed. LKQ. Oh, LKQ is equal to LPM. Wait, but I am not getting LKQ is, oh, LKQ. Okay. I was looking at LKM, which is 180 minus LKQ, and 180 minus QRP minus LPM. You are saying, so Rishan, how did you get, so did I make a mistake here while writing something? As usual, I would have made. Where did I go wrong in angle chasing? So you are claiming this is equal to this. You join PK, okay. By the way, K is not on the circle. You didn't use that, no? You join PK. Okay. I'm wondering what's wrong with mine though. Let me go over it carefully. I think I should also get it. It's just some standard angle chasing. LKM is KQL plus KLQ, exterior sum, which is correct. And KQL is MQL and MQL is MRL. So I said KQL is LRP, is that a mistake? No, LRP is KQL, that's correct. That's correct. And KLQ is RMQ. So KLQ is RMQ. That's also correct. Actually, we should write everything by directed angles, but for now, let's just write it. I mean, you just want to put the directed angle and we'll write it carefully. I think the proof will only then become correct, but for now, let's just ignore that. You can always put that later. LRP is QRP. What mistake did I make? LRP is Q. Is that a mistake? No, LRP is QRP minus. That is the mistake here, I think. LRP is QRP minus QRL. Okay, all right. QRP minus QRL. Okay, so QRL we can change it to QML. Okay, so now we can continue our calculation. No, Rishan, don't put alpha beta. Then you can't convert it to directed angle proof. Okay, that's why I write it in terms of this angle only. Even if it gets a little confusing to write these 3-letter symbols, I would say it's better you try to write it using this, because you can easily convert it to directed angle proof. Okay, just have to write it with orientations properly. Okay, so QRP is as it is, I guess. I don't know what to do with QRP. Okay, and QRL is QML. and RML is 180 minus, okay, so QLM you have QML and QLM, QR, is this correct? QRL is QML, that's correct. That's correct. So what about the second one, RMQ? Have I written it correctly? RMQ I have written as RML minus QML. Okay, so there will be two QMLs. So plus RML how to get inside? I think it's better to get inside the triangle. This plus 180 minus LMP. By the way, QRP is by it's just MLP. Okay, minus QML. So can we do something here? I think I should get the same answer as what Rishon did. Yeah, correct. You can always put alpha, beta, gamma, but then you have to write it with notation. That's correct. I'm just trying to see if I could directly write, but why? I mean, I should also get it right. What's wrong with this? There's nothing in this problem other than just chasing angles. I should also get it. Why am I not getting this? What am I losing? MLP, I'm getting two QMLs, which is annoying me. MLP minus 2 times QML. Is it, what is MLP minus 2 times QML? I don't know why I'm not getting this as well. Can anyone tell me what I can do to fix this? I think it matters which one you write actually. Oh no, nothing. We are just trying to show LKM is a fixed angle, Adi, and I'm just chasing angles actually without understanding what exactly should LKM be. I think Rishon says that he proved angle LKQ is equal to angle LPM, which means I have to just show LKQ is LPM. That means K is on the circle. Is that what you proved, Rishon? Wait. So Rishon essentially is saying that K is on the circle, right? How do you do this? Is that true? Rishon, didn't you say a few minutes ago that it's in your drawing K is not on the circle? In your drawing you saw that it was not on the circle. Ah, okay. So that means the problem is not yet solved. Yeah. So yeah, so we are trying to chase angles and see why LKM is constant. If the point is that if K is on a fixed circle, since L and M are fixed points in the problem, LKM must be a fixed angle. Yeah, you can try this by coordinate geometry as well, Abhi, but I think there should be a short angle chasing proof. Although the short angle chasing proof might take a long while to get, because you have to know what angles to chase correctly. Because you can break the angles in so many different ways here. I think we should not blindly do the manipulation. We should guess what that angle K is in some limiting situation or something. Can we come up with a limiting situation? In the symmetric case or something, like, what happens when P is along the line joining the center or something? Can we exactly tell what? Then it will become isosceles. Q and R are like, we can try to keep them equal. No, we may not be able to. That limiting case might be difficult. But can't we guess what happens if your P was here, if it's symmetric, right? Then by symmetry, it'll be something like this. Can we tell what it is? Or maybe it's not easy to write it in terms of the angle K. What if K is on the line joining the center? I think K will be on the line joining the center if P is on the line joining the centers, I think, by symmetry. But I guess the point is, you will get the formula in terms of some trigonometry and common chord. I think I don't think there is a simple way to solve it. I mean, there's no some nice function of angle, I guess, right? You can't really expect. That's the problem. So if you draw it's not in the middle. Okay. P, Q, R. Okay. What will this look like? If the common chord was D, then this is like D by 2. And this is alpha. I think you should be able to tell what this angle is. Then we are done. I think in terms of the radius or something, we should be able to tell. It's not some maybe simple expression. That's what I'm thinking now. Is there some other angle which is also remaining constant here? The angle subtended by Lm is alpha. So Lm itself is actually related to D, and alpha related to the radius of the second circle, the smaller circle. But what other radius? Abhi notes that the locus passes through L and M. As P varies over the circle S2, I guess when P coincides with L, then when P coincides with L, then what will happen is that this chord will just become the tangent. Okay, so P equal to Q will equal L, then you will get a tangent, right? And what will happen then? So maybe that is the case to consider. So Abhi notes that if I take draw the tangent, what will happen? What will happen if then P to R you can draw? Oh, but from P you have to draw one line passing through L and the other passing through M. If P coincides with M, then what is this? I mean, everything just falls. Now M is the same as R essentially, and MR is like, I don't know, it's confusing. M equal to R, this will become M comma R, this will become P comma L comma Q, and if you join L to R and M to Q, everything will just coincide. There won't be a K. I know. K is not ill defined, right? Because LR and QM intersect at infinitely many points. Just I don't see how that's helpful. So what do we do? How do we? We should have gone along the strategy only. LKM. What is a fixed circle on which K lies? Can we guess? Can we do some trigonometry and get the angle LKM as a fixed angle instead? Just assume radius R1, R2, distance D and everything. This chasing angle, I'm not so sure whether it will work. As P varies over the circle, the line segments PQ and PR and all will vary. What remains constant is not very clear. What is the plan? Any idea? LKM, LKQ. Can you do trigonometry and get it? What is looks so simple. There's nothing, there's no additional condition in this problem. Just almost everything is a construction, if you notice. There are no conditions. You just take a point P, join it to the two intersecting points, extend it to Q and R, join Q to M, L to R, and voila, whatever the intersection point is lies on a circle. Oh, power of a point. Oh, how do you use power of a? That's a very good problem question. How do we use power of a point to show that K lies on a fixed circle? The circle is unknown, so I guess you argue K lies on a fixed circle. How do you do this? Okay, but I want to do that trigonometry. I think there's some bit of angle chasing, bit of trigonometry kind of proof. If you could get what is that angle, Lm is like Lm by sine alpha is the radius of the second circle. Lm is r sine alpha, 2r sine alpha, where r is the radius of the second circle. But what, so what other angles do we know? Can we use QRM is equal to MLP and all somehow? QKR is but the circle is sort of, what is it saying? Circle is sort of known because it's a circumcircle of KLM. For any point K, you can always consider the circumcircle of KLM. That is true, but as P varies, how do we know K lies on a fixed circle? No, I'm asking how do you know, how do you use power of a point? I think you can use complex numbers. Oh, maybe you can. It's complex bash. Can you? This S1 circle can get messy. What about abridged coordinates or something? Can we do that? Like if you have S1 equal to 0, coordinate geometry, S2 equal to 0. I'm just trying different things. I think you guys should be trying and telling me what to do, different strategies. What do you guys think? Abhi is saying if you're going to complex bash, might as well do coordinate bash. No, not at all, Abhi. I mean, complex bash is way more powerful, remarkably powerful actually, if you're willing to do the algebra compared to coordinate bash. Maybe we should have a complex bash session. I should show you guys how to solve like using complex numbers. Like it's just too, generally it's too good. Like if you're willing, if you know how to arrange terms. Complex generally much easier. Yeah. S1 equal to 0, S2 equal to 0, the point P. Yeah. That's true. Abridged coordinates. I think this can be done by abridged coordinates, although I can't. It looks very abridged. I mean, there are two circles, there are two lines L1 and L2 given to you. L1 and L2, and then there is this L3 and L4. L3 is like QM and L4 is like LR, and they intersect at K. Yeah, very abridged coordinates setup it looks like. So if you look at the circle S2 and if you look at L1 and L2, then they all have P in common. L2 has L on it and S2 on it. So S2 minus alpha L1 L2 equal to 0 if you take. S2 equal to 0 is basically the equation of the circle, second circle. And L1 and L2 are equations of PQ and PR. And alpha is some real number. Okay, if alpha and L look alike, so let's call some K or something. S2 minus small k into L1 L2, where k is some, if you take this equation, you see that whatever this, this is a degree 2 equation, x square and y square. L1 L2 also has x and y in them, so this is also a degree 2 equation. So this is a conic, and this conic passes through P. So if you put P, this will vanish. and it has L on it because you know S2 and L1, S2 and L2 will vanish at L, and S2 and M will vanish at and for M will vanish on S2 and L1. So therefore M also lies on this. So P, L and M will lie on this for sure, whatever this conic is. And somehow I have to bring S1, L3, L4, L3, L4, L3, L4 vanishes at Q, L, M, R. S1 also vanishes. So some K dash is equal to 0 if you take. Then certainly all these 4 points will vanish on this. It's a conic passing through those 4 points. I have to prove K lies on a fixed circle. Should do some combination and get. I don't think it's that easy. Okay. No, I'll have to think about how to do the bridge. It'll take me some time. I guess it can be done. It looks. I think I need to get L1, L2, L3, L4 some condition. We have not yet imposed something. What have we not imposed? We have imposed everything. S1 and S2 have L and M in common. So by adding, subtracting and doing something we can. No. So Bisana is asking if okay, if you're doing coordinate you can simplify sort of, we can use coaxial circles with x-axis as central line, then write everything in 3 variables. Yeah, I think, I mean, I don't know how to use it properly, so it's not very clear. How do you do this? I want to do it by pure geometry, so I'm insisting. Yeah, if nothing works finally, I'll coordinate bash it, but I guess Abhi says that he got it using coordinate bash. But I would love to get this via pure geometry angle chasing. Does anyone have any suggestion? There are no tangents in this problem. Should I have maybe chosen something with tangents? LKM. Maybe I should have gone back to QRPs. MLP and MLP is 180 minus alpha minus LMP. LMP minus QML, maybe that is fixed. LMP. Can we see that? QML. RML. I'm going back to the drawing board. RML. I maybe should not have written as 180 minus LMP minus QRL. Just QRL is same as QML. So you'll just get QMR. So if I just group these two together, They came from different things. Yeah, maybe it'll work. So let's, I don't know, RML minus QRL. QRL. RML, notice guys, is RML, but QRL is QML. So if you subtract RML, QML from RML, you'll get QMR. Is it worth doing? Yes, I did. QRP plus QMR minus QML. QRP QMR, which by the way is QLR. This is QLR. So QLR minus QRP Rishan is saying the two intersections of the line joining the centers with S2. How will that help? Why can't I get this? Should we draw it on GeoGebra and check? Maybe that will help. Finally, GeoGebra, I'm giving up. Meaning, actually, we should draw accurately. Maybe that would have helped. That's why, so sad. It looked like a too simple a problem. I think when I will get the solution, I'll feel really bad. It's so simple. Let's draw. Oops. Okay. Okay. Here's a moving point. G is my moving point. Let's move it like this. So nice and we can move the points. Okay. HI. And what is it that we have to do? So I apologize guys for the spoiler with GeoGebra. But I think we have tried it enough. Okay, so J, and it is moving on one common circle. What is that common circle? How to figure out that point J? As Abhi notes, it will pass through the intersection points E and F, which means you can just, oh wait, does that mean I just have to pick 2 points J and J dash and show each? No, I think it's better to chase the angle. What is this angle? Show head object. Let's move on center a bit. Yeah, this is a BMO problem. So what is Rishan saying? The two intersection line joining centers, just to that help, I guess. The limiting case of P. What is this angle? Oops. What is this angle? Twenty 28.73. Let's make it 120, it's 32.5. If it's 90, it is 12. I don't know, maybe it's not so simple to guess what the answer is. You have to do by trigonometry or something, not usual angle chasing. Maybe by inversion or something, because as you get C closer, it's becoming larger if you go out. I don't know. I don't know how to do this. If you move the point symmetrically, oh no, so it's not a function of this alone, right? Obviously, as expected. I thought so, but we needed to prove it. See, notice you get angle is 120 again, EJF, but beta is 18. But some other place you can again get 120. You will not get 18, I think. That time we got something, we did something. Now it's 15. So it's actually a function of many other things, the radius and so on. So we don't just have a dumb angle chasing technique, at least whatever I was trying, obviously was too naive, right? Because it is a function of, it will remain constant as g varies, but this angle is a function of many other things. You have to do some trigonometry, I think, at this point. No, Abhi, but the point is that if it was purely some angle chasing proof like this, see, we'll know when this kind of proofs fail, okay? If I wanted to just start with LKM, do some blah 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 blah, and finally get something as constant, then that wouldn't depend on the radius, no? The argument, then the angle, I mean, whatever is the angle then will purely be a function of this angle. It will not be a function of the radius as well. But it has to be a function of radius or some other thing, because we noted that this angle was changing for a given fixed angle here. Right? So if you try to draw with the compass and actually in the exam, before even trying such a strategy, I think that's the thing we should do. Even before trying such a strategy of just dumb angle chasing, you should draw multiple drawings quickly and check whether the angles are changing, because you don't have GeoGebra at your disposal. So you should be actually drawing by compass and strategy very quickly. You can draw this is very easy to draw. Multiple circle, like 5-6 drawings, diagrams you should draw and make experiments and guess whether this angle is changing. I mean, for the same angle, whether you're getting different angles and so on. And if you get it, then the strategy is doomed. Okay, so we have to come up with some other strategy now. Either, of course, you can always do coordinate geometry, but is there somehow we should try to get this angle as constant as a function of, basically name this angle theta or something and start chasing angles and finally get whatever, some sin theta cos theta is equal to some fixed quantity. That's the plan. That's what we should do. Call LKM theta and then chase angles. I mean, then do sine rule or something. That's my next strategy at least. Can we apply sine rule in multiple things and get something? So what is the question I just joined? Shreyas Pujari asks. Yeah, you can see the question on the screen now, I think. Right, so what do we do now? Lm by sine alpha is 2r, but if this is theta, then 2r sine alpha, which is fixed, by sine theta is, well, this is what we have to prove is fixed, is equal to some Lk by this angle, and Lk by that sine of that angle, sine of this angle is same as sine of this angle. We have to somehow get which year BMO problem is this? Oh, I don't remember. I picked from random BMO problems, 2003. Maybe this looks like a newer BMO, maybe. No, maybe it's an older one. I'm not sure. I should have written the name. I'm sorry, I'm sure if you Google it, you will get it. Which year BMO it is. Is it there in my screen right now? No. Yeah, it's there, it's there. It's BMO 2010, round 1. BMO 2010. Wait, where is my screen? Okay. BMO 20, yeah, as Abhi has written. I do not know how to solve this problem. Okay, I think I should give up officially now. I officially give up unless someone comes. So maybe in YouTube or any other place you can just write to me with the solution that you get. I would like to see a solution that uses trigonometry, if you can. Or maybe there's a really cool pure geometry proof of this. This problem looks really nice. How do we solve this problem? No theorems seem to be useful other than angles in the same segment are equal and opposite angles add up to 180. Oh, Adi remembers then Adi, it can't be, obviously it can't be a function of just LPM. Some other thing is also remaining constant here. I don't know what it is though. I guess the angle subtended by LM on the other side also. Maybe that is the thing. Maybe is that the, oh, I think it's true. Is that the point? LM subtends P here, but LM is also a common chord, right? So this chord will subtend some fixed angle on this side also. Now, even if P varies, this angle won't vary actually. Maybe that is the point, this beta won't vary. This will be beta. But even if the point P varies, it will remain beta. So it's a function of alpha and beta, I think. And then it will just be a pure angle change, and I'm just missing that. Maybe is that try to write everything in terms of alpha and beta, and we are done. Something like that. Yeah. MLP, I think so. So can we just revisit? I think we can finish it. That was the maybe the missing point. Come on. Oh, if that is the case, I really have to beat my head at the wall. So QRP, okay, maybe we can finish it off. So LQM, let's see now. I never thought of writing it in terms of just those two. So, okay. So LKM is KQL. Let's revisit. KQL, which is beta, awesome, fixed, plus KLQ, very good, and KLQ is same as RMQ, very good. LRP is also beta, and you don't need this nonsense. This is beta, we know it's already a fixed constant, a piece we have removed. RMQ is RML minus QML, RML minus QML, and RMQ, I think I have to KLQ. Yeah, the answer should be a function of both the circles. That's correct. RMQ. Guys, what is RMQ? RMQ is 180 minus QMP. Done. What? Stupid. Was it stupid? I was stupid. What is this nonsense? That's all? I'm so stupid. RMQ is 180 minus QMP. 180 minus angle QMP. Right? And QMP, 180 minus QMP is just what? In the triangle QMP is alpha plus beta. So alpha plus 2 beta, done. So LKM is constant. Yay. Okay, is this correct? So should I go over the proof? Actually, it was too easy. Looks like. I just missed. Yeah, it's just too easy. So what was the main point? Obviously, as we noted, I mean, the main thing we should have realized, such a stupid thing, we should have realized that LM is a common chord. So obviously the angle subtended by LM in both the circles is fixed. It is some angle. Of course, you can use trigonometry and all, write it as 2r sine alpha or something, but it doesn't matter. It's a fixed angle. Let's just call that angle alpha and beta. One subtended in circle S2 and the other one circle S1. And once you get that, it's so easy angle chase. Angle LKM is, let me repeat, LKM by exterior sum is KQL plus QLK, but QLK is same as QMR, this one, RMQ. And once you get RMQ, you know that is nothing but 180 minus QM. I mean, directly you could have written actually. RMQ by exterior sum is alpha plus beta. You don't even have to write this step. This like BMO has the same solution. Just wasted an hour, I think, on chasing, and it was so simple. Of course, you have to actually finally write it using directed angles, I think, or else, you know, as you move around, that alpha will become 180 minus alpha at some point, and then the configuration will look completely different, and then your proof will fail. So your proof will be incomplete. So in the exam, you will not get marks, right? And it's a big problem. So you should write this carefully using directed angles. Should not be a big problem. Right. I didn't know that BMO has solutions. I thought BMO has no solutions. Do they release solutions for old things? Okay, maybe that's what Adi is discussing. Alright, so I'll stop today. So you guys can take a snapshot of this and try it. Or maybe I'll try to put up this one on the I'll put it as a post on the Ha Problems channel, and you guys can tell me, put hints of how to solve. This also is a old BMO question. I think BMO is like RMO. Okay, alright guys. So I will try to put a poll on what you would like to see next. I guess complex bashing and all are very good techniques to see. But I think combinatorial configuration problems are also fun. So we should be able to do those. Okay. Alright. So it's lively chat going on. So let's meet on Saturday then. Okay. So maybe I'll put a poll on what you guys would like to do, and depending on the poll, I'll take the session on Saturday. Okay. All right. See you guys. Bye.